Hello everyone, my name is Junhao Dong. I'm glad to introduce our paper accepted by ICCV this year, Robustifying Zero-Shot Vision Language Models by Subspaces Alignment. And here I will introduce the background of adversarial examples and visual language models. Adversarial examples are specifically crafted inputs designed to confuse neural networks. Although these adversarial examples appear visually similar to natural examples, they can cause significant disruption during the inference stage. For instance, like this panda image, by adding an undetectable perturbation to an image of a panda, we can create an adversarial example that causes a high-confidence misclassification. Technically, these examples can be obtained through image-level gradient ascent. In addition to single model architectures, such adversarial threat can be even more harmful to cause a significant disruption to visual language models. Enhancements of zero-shot robustness of VLMs focus on adversarial fine-tuning and rely on sample-wise feature-level alignment between each adversarial examples and the static text prompt class target, which inevitably force to capture distribution chains of groups of related samples. For example, augmented samples of a given image is thus degrade the robustness of zero-shot inference on unseen adversarial examples. At test time, the robust accuracy for augmented test samples drop faster with respect to adversarial attack radius than for non-augmented text examples, creating a gap due to variations of test or chain augmentations. It further exacerbated by adversarial attacks. For our method, aligning subspaces equals aligning all samples that could lie on each subspace. Even if they are not in the dataset, it can still lead to better robustness or smaller gaps. Instead of sample-wise adversarial fine-tuning, we use a second-order variant. This figure shows how subspaces handle points as groups. As the fixed nature of text prompts with respect to the ground truth class also affects the trade-off between natural performance and robustness, we generate adversaries by perturbing both the vision and text branches simultaneously, yielding challenging joint adversaries. Our theorems also show that our subspace alignments improves localized Lipschitz smoothness, and our used MaxEXP approximation is also stable and robust across diverse scenarios. And here we use clip to encode both size and image set, original plus standard augmentations and text prompts. We learn a universal adversarial set perturbation for images and for text. This generates intermediate and final adversaries for each modality. From the image set, we compute claim versus adversarial covariances. From the test sets, we build class subspaces while MaxEXP for each class. A subspace level classifier that aligns each image subspace from clean to intermediate to final towards the target class subspace and away from non-targets. And we jointly shape images and prompts so the image subspace lands where the correct text subspace lives, thus improving robustness alignment. And here we show that our method achieves improved zero-shot performance in terms of clean accuracy and robustness against adversarial examples. And here we also show that our method can further extend beyond zero-shot classification to image captioning, image text retrieval, and even medical image analysis. So here we summarize the contributions based on our observation that augmented adversaries tend to deviate more significantly in the feature space. We propose the first subspace aligning adversary methods to match their chains, which means the second order moments rather than individual samples. And we further introduce subspace alignment from embeddings of a class category text prompt with synonyms prompts. We also design a joint adversary generation scheme to find the worst case adversaries. And aligning these adversarial subspaces further achieve a better performance in terms of robustness and clean accuracy. That's all about it. Thank you.